guess take it away. Thank you.
Awesome. Yeah, so hi everyone. I'm really excited to share today with you our talk on Architecture 2.0. My name is Shvetank Prakash, and I'm a third-year PhD student at Harvard, working with Professor Vijay Janapa Reddi, who unfortunately couldn't be here today, but I know he's also really excited to hear all your folks' response on this topic. And today's talk is not going to necessarily present a single resource or solution, but rather more so aims to ask some questions that we would like to get us all thinking about surrounding generative AI and hardware design. But before I dive in, I just want to give credit first to the large number of people that have all contributed to what I'm about to share. Many folks. Couldn't even fit everyone on the slide, but yeah, this is definitely a collaborative effort. So let's begin first by revisiting Architecture 1.0. So traditionally, in Architecture 1.0, innovation in the systems has historically been driven by TAO, technology innovation, architectural innovation, and optimization. By technology innovation, I mean development in process nodes thanks to Moore's law and Dennard scaling. And historically, architectural innovation has been driven by hardware support for parallelism, such as instruction-level parallelism, thread-level parallelism, data-level parallelism, and so on and so forth. Optimization, which we can say is in the form of better managed runtimes or vanilla compiler optimizations, and we've also done full-stack hardware-software co-design. But with the plethora of emerging applications with demanding requirements, we are increasingly starting to build more complex and specialized systems. And as John Hennessy and David Patterson, Turing Awards winners famously said, we are now in the era of domain-specific computing. But as we're all aware here, designing such specialized hardware is very challenging due to high costs, long development cycles, and error risks. And so what this talk aims to get us all thinking about is how we can use AI to help us overcome this. So enter Architecture 2.0, which aims to address these challenges and democratize hardware design by leveraging open source foundation models, hardware-oriented datasets, and generative AI. So we loosely define Architecture 2.0 as the era in which we use AI and ML methods to minimize human intervention, build more complex, efficient systems in a shorter time frame. So now recently, we've seen with the advent of all these large language models and these AI systems that are the state of the art nowadays, how we can essentially train on a bunch of data in various sources like text, images, and speech, and then we can achieve some pretty revolutionary tasks such as image generation, audio generation, and text and code generation even. And so ChatGPT, for example, can even try to build you a RISC-V simulator. And I'm assuming probably everyone here at some point has also tried and experimented with its RTL generation abilities. You know, that's questionable and subject to debate, but you know, we've all done that. So we've seen the opportunity that exists with these foundation models for many other domains. But what about creating foundation models that can help us with system design? Or in other words, can we create data sets for hardware design to create foundation models that can help us design better systems? So we envision a future where one day you may be able to walk up to a computer and prompt it with something like this. Act like an architect, design me a custom 64-bit RISC-V processor with full vector extension support and optimize it for less than 3-watt TDP in a 7-nanometer low-power process node using the TSMC plugin library. Now, that may seem far-fetched at the moment, but we believe this is the North Star that we should be aiming towards to make progress. However, there are many challenges with realizing such a future, and we actually hosted a workshop with the community to help us break down and address these challenges. And so the rest of my talk now is going to be diving into those. And while we don't necessarily have all the solutions right now, we believe these are all important pillars for us to think about. So the first challenge is data sets. And so ImageNet, if you're all familiar with, really drove the ML community using competitions, and it was essentially a very large crowdsourced data set on images. And pretty much all we owe today in terms of ML can largely be attributed to ImageNet. However, in hardware, we don't necessarily have these large and high quality publicly available data sets, and we also have to figure out how to manage and balance sharing data while also dealing with IP issues. We also don't have the ability to scrape like you can do for all these other corpuses. So, ImageNet, for example, any sort of Wikipedia data set, all of those, you have the ability to scrape the internet, but we don't have that ability in hardware, and so what we rely on is simulators for collecting data. But there's this trade-off now that we have within simulators, from cycle-accurate simulators to analytical models, trading off speed for accuracy. And so we have to think about how we can balance this nuance when trying to leverage ML for system design. Next is ML algorithms. And so the ML algorithm landscape is rapidly evolving. And there's everything from heuristic algorithms to supervised learning, unsupervised learning, reinforcement learning, semi-supervised learning. And the question we ask ourselves is, how do we compare these algorithms fairly against one another? Even within, for example, reinforcement learning, we have all these different paradigms, for example, such as value optimization, policy optimization, and imitation learning. So this makes it very challenging for us to progress as a field. And so what we need to do is identify what the best practices are when applying ML to hardware design, more broadly speaking. But right now, it's still quite unclear at the moment what are the best practices for applying ML algorithms to architecture and hardware problems. And so there's many different things for us to consider, such as, is this a high dimension or low dimensionality problem? What are the constraints? Is it a discrete or continuous problem? And so essentially, we need a playbook like this to help us understand how we can actually apply ML to hardware design. And so here are some of the challenges and questions that we deal with in designing systems that the playbook would potentially need to address. Next is tools and infrastructure. So simulators are the backbone of a lot of the research that we do as a community, and it has driven much of the innovation that we see today. But for this next generation of ML-driven hardware design, we need to think about how we can use ML algorithms and interface them with our simulators. And so we need to be able to decouple the hardware components from the ML components to allow both communities, folks coming from the ML side, folks coming from the hardware side, to make progress while also maintaining systematic evaluation. And so we actually built some infrastructure and a tool in which you can use any sort of ML algorithm and have it interface with any sort of hardware tool or simulator. And so we've built these sort of environments for tools like OpenLane and so on and so forth, and all the kind of open source simulators out there. But this allows us to create one unified framework in which we can systematically evaluate progress. And so the tool was called ArcGym and actually presented at ISCA, which is Computer Architecture Conference, in 23, so last year. And so while there were multiple contributions of the paper, there are some of the key ones listed here, which is essentially, it enables ML-aided design space exploration, but more importantly, it fosters systematic evaluation and comparison of algorithms. If you look at kind of past works and research in this space, all the papers have different setups, different hyperparameter settings, different algorithms, all claiming that X algorithm is better than X at providing Y performance improvements. But what our paper actually showed is that essentially all algorithms are equally favorable at finding optimal solutions. And so what we need to do is actually think about how we're systematically evaluating these, and hence the framework, so that we can make sure everyone has the same setup. And the other piece that came out of this framework is the ability to create public data sets. And so our paper, looking at kind of the challenges I've outlined, attempts to address many of the challenges for design space exploration using machine learning. But this is just one of the tasks that we may possibly want to use. And this is obviously not the end-all, be-all solution. So lastly, I'm not going to go too much into it, but we also need to think about how is ML-aided design and using generative AI for our design going to affect workforce and training? And so questions we need to ask ourselves are, what do hardware designers need to learn to facilitate ML for computer architecture? Or what training is required to enable machine learning into our workforce? How do we need to change education potentially to train students so they're prepared to use these technologies and also empower them to become better developers? As we all know, there's kind of right now a shortage of people who are working on this, students studying this stuff. So how can we use AI to empower them so we can increase productivity and the ability? And so that outlines kind of some of the challenges that the community has aligned on in terms of what we need to tackle if we're going to really realize these open source foundation models. And so if we want to have an impact and make progress in this era of AI and ML, we need to build a community, though, and this is in this way we can all achieve collective gains. So more importantly, though, we need to adopt open source practices in developing foundation models and data sets that will accelerate progress, foster collaboration, and ensure the benefits of this approach is accessible to all. So we believe the open source hardware community will be instrumental in realizing Architecture 2.0, empowering designers with open source tools, data sets, and methodologies to create accessible, efficient, and innovative hardware solutions. So if you're curious to learn more, here are some QR codes for some past events that we've hosted, including some blog posts we posted, as well as the community workshop. And so in which many folks from both academia as well as industry participated in and have collaborated to help us foster this idea. Eventually, we would like to build an open source community like this with challenges, competitions, etc., leaderboards that can help the field progress towards open source foundation models. So we've come a long way since the initial blog posts, and then we also had the workshop. We've also got interest from OCP, and we've started working on a white paper now on which kind of crafting this vision. And this summer now we're actually going to work on getting started on a large crowdsourcing effort that the open source community is definitely needed for. So if you're interested in joining the community, please feel free to fill out this form. And thank you for your time.
All right. This is a very large, broad, interesting area that you're covering here. My first question is, where do you get the impression that the best bang for buck is right now?
I mean, I think at the moment, as far as what we've seen, it's pretty much RTL code generation. But I think that's quite limiting and a small goal, right? I think that's one way in which hardware designers design systems. But there's many other things that we do as well, right? You profile systems, right? You need to optimize them, and so thinking about how we can, use these technologies to do other things like design space exploration, or one-shot profiling, those sorts of things, I think would start to then, realize what actually a foundation model for hardware design would do, right? There's not just one task that we do.
What about working backwards? So what about using AI and ML like machine code generation in a compiler or something?
Yeah, so that's actually, we broadly, so we call it Architecture 2.0, but we, broadly speaking, include all of those things. It can be used for things definitely like code optimization, cloud scheduling, accelerator design. We kind of, and even EDA optimizations. We don't really want to limit ourselves to just architecture, and the community itself is comprised of people all across the stack. So definitely lots of opportunity there to leverage and explore this technology. But we definitely need kind of help and feedback from the community as to what are those actually downstream tasks that are actually relevant. So if we look at this foundation model here, right? So there's a bunch of different tasks that this foundation model can achieve for image, text, etc. But what are the things that we actually care about a foundation model being able to do for us, right? Yeah, sure, RTL generation's one, but there's many more other things that potentially we could leverage it for to empower designers. And so that's something I think as a community, especially as an open source community, we can really do a good job at crafting and understanding.
Yeah, cool. And final question from my side is, what is the first tangible outcome you guys want to see? Like,
Yeah.
what do you want to demo?
Yeah, so first tangible outcome, I mean, all of this still comes back down to data, right? In order to realize any of this, data is the first building block we need, right? And then from there, right, creating some probably sort of fine-tuned model that can achieve, improved performance on, again, those tasks have to be somewhat outlined, I feel like, among the community, but RTL generation is one, but also like, design space exploration. Imagine if I could actually ask a model like, hey, how does this hardware performance compare to this other system for a certain workload I'm interested in, right?
Yeah, cool. Questions?
So it seems you're very focused on chip design. Have you thought about just going to something like Octopart and looking at spec sheets and training about, I'm sure we've all been in this position before, what chips can we switch out if we don't have orderable quantities that we need to build a specific board or to build a specific architecture?
Yeah, so I think what you're describing kind of falls under design space exploration in my head, kind of as in like, imagine you have essentially a plethora of options and you're kind of trying to figure out what is the best option to slot in there, right? So it's almost like a parameter selection problem, right? And so say you're limited, you're limiting in this case just the design space to remove a piece that you may be short of, right? But you're trying to find that. And so actually our ArcGIM actually already facilitates that. So essentially, ArcGIM here just has this generic interface where, you essentially build a wrapper around whatever problem you want, whether that be a simulator, whether that be exactly what you described. If you can somehow formulate that as an environment, then you can just interface it with any ML agent, and you just need to expose the right parameters. In this case, what you're saying, like the spec values. And so, a machine learning agent is then going to try to optimize for that spec, right, in the form of a reward signal. So that's how reinforcement learning and so on and so forth is done. So this is actually doable probably in this current framework that we have already. But yeah, I think it's definitely a good use case as well, because there's a lot of trade-offs we try to manually assess, in which an ML agent can definitely bootstrap that.
Have you tried using ML for UVM or design verification, or explored this at all? Because you could probably go from a design spec to a bunch of tests and stuff, and UVM is basically a language that's just entirely boilerplate anyways.
Yeah, so we, myself personally, and we haven't yet necessarily, but there are, again, this is a large community effort, and if we just kind of look on the right here, I guess, all the different kind of pieces involved in kind of actually designing a chip, the cost is attributed to many things, verification, software, all those things. And so people have actually looked at that. I think people from Microsoft have looked at specifically what you're mentioning. And so there's definitely a lot of different use cases in which you can potentially use this across the design process. So yeah.
Very interested in this idea of looking at, oh my God, I don't have this part in my design.
Mm-hmm.
If I have a design in KiCad and I have data sheets from several manufacturers, that actually sounds like a really interesting solution that would be immediately available today if you could, that people would buy and pay for it.
Yeah.
There are small companies in that space. And you can get some things like the hardware and custom product specific to get data sheet from various LLMs and do that. Yeah, so being the open source guy here, I've been doing embedded Linux for 20 years. And the last thing I'm ever going to do is use an AI model or a cloud-hosted AI model. So the question I want to know is, first of all, can I get the permission from the vendors of the data sheets
Right.
to train an open AI model?
Mm-hmm.
That would be my first step. And then, what is the hardware requirement? If I was going to tape out chips at Skywater Foundry,
Mm-hmm.
how many wafers would I need to take? How many wafers would I need to produce to build a machine to train the AI on something I can build with an open RISC-V design that I can tape out and say this entire stack from top to bottom is source code I can point to?
Yeah. So no, those are all great questions.
Sorry, Shvetank, can I just summarize the question, which is, how far are we away from having a full stack of this, like of the actual AI ML?
Well, I'm thinking, what would we need to have the full stack to say, okay, I have a design in KiCad, I have a bill of materials, and I have the data sheets for the parts. Then, how far are we from being able to have permission from all the vendors that want to sell us parts to be able to have an AI select alternative replacement parts?
Yeah, so I think this kind of comes back to it's a great question, and I think these are definitely some of the challenges to come, and you're like definitely hitting on the nail. Definitely this issue with like IP definitely is going, and how we keep things private and how companies allow us to potentially use data and so on and so forth is something as a community we have to figure out how we can balance that trade-off between, you know, making things public while also, you know, keeping certain things confidential. We have definitely spoken with the community, as I kind of put at the end there, and there's a lot of industry folks who are interested in this, and they also understand, you know, what the open source gives back to them as well. So we have also started, you know, beginning discussions into like thinking about ways in which we can balance this trade-off between, you know, keeping stuff private and also creating these open source models. So definitely something that needs to be addressed if we are going to realize this. Because currently there are companies that have actually built some internal versions of, you know, foundation models. For example, NVIDIA built ChipNemo, which is kind of, they just took all their internal kind of data and trained a foundation model. And so, yeah, it's definitely, you know, a question, I think a very relevant question and something that needs to be addressed. I don't have the answer today, but I think as a community, we have to all think about that and how we can address that.
Amazing. I think we're out of time, but there's the Matrix chat. Thanks, Shvetank. Thanks very much.
Awesome. Thank you so much, folks.